It's a final year PhD student at the National Astronomical Observatory of China. He has been working on the Einstein Probe mission, and he has been visiting since February of 2025. Yes. So today he will present to us the discovery of a neutron-star X-ray binary with the Einstein Probe mission. So, floor is yours.
Thank you very much for the introduction. My name is Yilong, and if you need help to remember, it's kind of like the name of Elon Musk, but not really the same because my name is Chinese, and his name is not Chinese. And so it's actually going to be my last PISA seminar before I return to China next week. So I thought it'd be nice for me to talk about my own work that I've done during my visit. And it's mostly on this new neutron-star X-ray binary, which we discovered with the Einstein Probe. Oh no. Maybe. Okay. So before everything, I will introduce the Einstein Probe mission itself. The Einstein Probe, or EP, is a time domain space observatory operating in the soft X-ray band. The main scientific objective of the mission is to discover new soft X-ray transients and monitor the variability of known sources with the all-sky monitor on board. And EP is also equipped with a follow-up X-ray telescope, which can perform deeper observations for the transients discovered by the monitor. And the EP is also capable of sending out alerts to the international community to tell people about the new discoveries. The mission was first proposed in 2012 and adopted formally in 2017. And it is led by the Chinese Academy of Sciences, but later joined by ESA and MPE in Germany in 2018. And later in 2022, NS in France also joined the collaboration. And in the July of 2022, a Pathfinder project, which is an experimental project that is essentially a smaller version of WXT, of EP, was launched into space and to test if everything works normally as expected. And the project is named Laia, like the princess. And finally, on January 9, 2024, EP itself was launched from Xichang, which is in southwestern China, and it was launched into space, carried by a Chinese Long March rocket. And it was a very emotional day for all of us. And even though by we, I meant the other students and me in the group, even though we were a little bit upset because we were not invited to watch the launch, but still we went to a fancy restaurant and had an expensive dinner to celebrate. And I need to complain. I'm to complain about not being invited. Oh, and in this picture, you can see the cloud that's left by the rocket. And if you try really hard and if you really want to see it, you can see it looks like a dragon, a Chinese dragon, not the Western dragon with wings. And because 2024 was the year of dragon, so it was considered as a very good sign for the mission to be successful. Now I have a cool video about of the launch. And this is a telescope, but it's not as cool as launch, so I was good. The satellite carries two telescopes, two X-ray telescopes. The most important one is the wide field X-ray telescope, WXT, and it is composed of 12 identical modules. They are those white squares surrounding in the edge of the satellite. 12 identical modules, and as the name suggests, the wide field X-ray telescope has a wide field, and it is equipped with a novel technology called the lobster eye micropole optics, and it gives WXT a very large field of view of over 3,600 square degrees. It operates in the soft X-ray. By soft, I mean low energy X-ray band. So soft X-ray energy band from 0.5 to 4 keV. and it has a reasonable resolution of 5 arc-minute. And the sensitivity is also not too bad, considering it has such a large field of view. And the other telescope is a follow-up X-ray telescope. And as the name suggests, it follow-ups everything that is discovered by the WXT. And it is a more conventional water-worn type telescope and has a smaller field of view, but a higher resolution and a higher effective area. And the bandwidth is also wider. It covers from 0.3 to 10 keV. So generally, the WXT detects new sources, and the WXT follows up. Now, this slide shows the technology that is used by the WXT. You can see it's a picture of the lobster and the eye of the lobster. It is very different from our eyes. It is basically made up of many small holes, like micropores, and it is exactly the same geometry used in the MPO plates of WXT. And you can see the WXT optics is made up many small holes with a diameter of roughly 40 micrometers. And this cartoon shows how it works. Basically, the X-ray photons bounce off the walls of the micropoles, and depending on how many times it bounces off the walls, it will land in a cross-like shape. So a point source would be a cross in the WXT image. And this shows actually the first black image of WXT. The background, the more colorful background, is actually optical, and the X-ray data is blue and purple reddish image. And you can see there are many crosses in the sky. They are all the important and the very well-known X-ray sources in our center of the galaxy. And the yellow, not very clear here, the yellow squares are the field of view of WXT. And I have another video that shows the monitoring of WXT in one single day. So you can see how the WXT covers the entire visible sky multiple times within 24 hours. Okay, the surrounding area were not observed because they are too close to the sun, but after 6 months, they will be covered. And this shows the all-sky image collected by WXT in the last 2 years. You can see the blue belt is our galaxy, and you can even see the Fermi bubble here. And this is a summary of all the discoveries made by Einstein Probe in the first 2 years of its operation. It discovered over 170 new X-ray transients and 1,500 stellar flares, published over 200 papers, and sent out 500 observatories. And you probably already noticed this Monday, there is a new paper in arXiv, which is basically the statistics of all the papers sent to arXiv in 2025. And according to this work, the Einstein Probe is the most highly cited telescope in 2025. Of course, citations don't mean everything, but it still shows the impact of the mission. Finally, I want to introduce the data policy. The EP data are proprietary for 1 year after the initial observation, and after that, they will be released to the public. Now, the first batch, starting from last December, actually, the first batch of WXT data are already available, and WXT data will also be released in this year. That's early 2026, which is pretty much now, but I'm not sure whether anyone is reading this year. And the data can be downloaded from the ICE-CSIC page of Einstein Probe. You can find it, I think, easily, just Google it. Now I will give a more general introduction to neutron-star low-mass X-ray binaries as a whole. The low-mass X-ray binaries are binary systems composed of a neutron star or black hole and a low-mass star companion. So it's a neutron star or black hole plus a normal star. And the star is low mass, which means it has a mass equal or less than our solar mass. And the emission in the system is mostly powered by accretion from the companion star, by accretion of the gas from the companion star. And it emits mostly in X-ray band. So that's why they're called X-ray binaries. And most of the low mass X-ray binaries are transient systems, which means for most of the time, they are not visible. They have very long quiescent states lasting for years. And then when they go into outbursts, the outbursts usually last for several months, or sometimes several weeks. And to date, we have, by we, I mean all human beings, we have discovered over 200 low mass X-ray binaries, and 2/3 of them are neutron star low mass X-ray binaries. So they outnumber the black holes. And this shows this cartoon shows the geometry of the accretion happening around the neutron star. So this is the neutron star, and this blue thing is an accretion disk. It is formed from so the neutron star has a companion, and the companion can fill up its Roche-lobe, and any extra gas can flows from the inner Lagrangian point and get captured by the gravity of the neutron star or black hole, and it forms a disk around the system. It's called an accretion disk, and it emits this is the spectrum of a neutron star mass binary. It emits a disk black body spectrum, and it's called a multicolor black body because in each different radius of the accretion disk, the temperature is different. So it has its own black body spectrum corresponding to its local temperature. And when you sum all the emissions from all the radii of the disk, you get what is called a multicolor or multi-temperature black body, which is this blue line here. And inside the accretion disk, there's this pinkish thing called a corona. It is, I should mention, the disk is geometrically thin. It's thinner than this cartoon. It's geometrically thin, but optically thick. And the corona is the opposite. It is geometrically thick, but optically thin. And it has many high temperature electrons inside this cloud. The temperature can be as high as the order of 9 to the 10 keV, more or less. And it emits Comptonized emission. I will explain later. And the neutron star itself, when the accretion flow hits the neutron star, it creates some hot region in the surface of the neutron star, and it emits a normal black body spectrum shown here. And but the black body emissions from the neutron star and the disk, they are kind of low energy as compared to the hot electrons in the corona. So when the soft photons, the low energy photons from a disk and from neutron star enters the cloud, it will collide with the high energy electrons. And because the electrons are actually more energetic than the photons actually gain energy from these collisions, and they are called inverse Compton scatterings, as opposed to normal Compton scatterings, where the photons lose energy. So when the photons leave the cloud, they are more energetic, and they form a power law-shaped spectrum here, which is called the Comptonization spectrum. And from the other direction, the emissions from the corona can also be intercepted by the accretion disk, because the disk is huge and it blocks the emissions. And when the high energy X-ray from the corona hits the accretion disk, it'll be absorbed and re-emitted, and it forms this reflection spectrum. And you can see it's kind of irregular because there are many lines overlaid to the continuum spectrum. That's a general picture of the accretion. And here I want to introduce a very typical phenomena that we observe in neutron star low mass binaries. They are type 1 X-ray that they are called type 1 X-ray bursts. So when the gas is accreted and it accumulates on top of the neutron star surface, when there are enough matter accumulated on top of the neutron star surface, the temperature and the density gets too high, and at one point it triggers thermonuclear runaway, which is kind of like novae in white dwarfs. And it's typical only for neutron stars. Black holes don't have it because it doesn't have a surface. And here I show some of the light curves from our sources, from the known low mass X binaries, and those are all type 1 X-ray bursts. And you can see the duration. Probably you cannot see because it's very small. The durations can be very different. This burst lasts for over 500 seconds, while this one only 12, 14 seconds. The duration of the bursts, and I should mention, they usually have a fast rise and exponential decay profile. And the duration of the burst is usually associated with the composition of the field. Generally, if the field has more hydrogen, the burst would last longer. And if helium dominates, then the bursts are shorter. And the spectrum of the bursts is usually well described by a black body spectrum, and from a region of 1 to 10 kilometer radius. It's roughly the size of a neutron star or a smaller spot on the neutron star surface. And there's another thing I like to introduce. It's called photospheric radius expansion, PRE. It's a special phenomenon which happens when the luminosity of the burst gets so high that it reaches what we call the Eddington limit. The Eddington limit is a critical luminosity when the radiation pressure of the photons balance the gravitational force of the neutron star. So as you can imagine, if the luminosity gets higher than its limit, radiation pressure would be so high that the neutron star can no longer constrain the matter surrounding it. So for example, you can see this burst. It is a PRE burst. When the first panel shows the luminosity of the burst, and you can see when the luminosity reaches its peak, now this one is temperature. The temperature starts to drop, and this is the radius of the black body region. It increases while the temperature drops. It's because when the luminosity gets so high, the photosphere of the neutron star expands because of the radiation pressure. And at the same time, temperature drops because the total energy released should be more or less the same. So the black body temperature, which should be the effective temperature, drops as the radius expands. And it tells us important information that the burst luminosity is at the Eddington value. And the Eddington value is pretty much a constant. It depends on the mass of the neutron star. So in a sense, we can tell from this luminosity that what is the distance of the source based on the observed flux. But it didn't happen to our source. I was just giving a general introduction. And I want to mention the bursts, they repeat, but usually they don't repeat regularly. Usually they are irregular. And when I say usually, it means sometimes they are regular, which is the case for our source. Now I can finally introduce our own work. So this is the name of the source we discovered, and I don't want to read this. It's its address. It's the location in the sky. And from now, I will call it the clock burster for reasons I will explain very soon. The clock burster was detected by WXB last June 23, and I was in Italy having pasta. And it happened, and we were very busy because of it. So it was detected in June 23, and 2 days later, the students who were on duty at the Einstein Probe Science Center, his name is Nikon Ray, he identified the source as a new transient and submitted the first FXC follow-up. It was 2 days after the detection. And in another day, on the 26th, they sent out an alert to the international community from the astronomers' telegram, and it triggered multi-wavelength follow-up. We ourselves, we monitored the source with EPFXC from June 25 until August, when the source fades back into quiescence. We observe the source daily with FXC, and there are also SWIFT observation, which is another type X-ray telescope. SWIFT also observed the source for 18 times since June, and on June 27, we also asked for a NuSTAR observation, which is another X-ray telescope, and I will introduce it. We observed the source with NuSTAR and had a 47 kilosecond exposure. And in the radio band, NeoCat detected the radio counterpart, and in the optical band, SWARM detected the optical counterpart. And we also observed it with the UltraCam on the NTT which is optical telescope, and I will introduce because the yellow ones are the ones I used in my work. So this light curve shows the this is the first this is the light curve of the first FXT follow-up observations, and you can see it's very extraordinary. First, we see something that looks like an eclipse here, and what looks like a type 1 exoburst with a fast rise and a slower decay, and this with the fact that the transient is located at a galactic latitude of 3, which is very small, means the transient, the source, is located within our galactic plane. So it is very likely that it is an eclipsing neutron-star low-mass binary. It is eclipsing because we see the eclipse, and it is a neutron-star low-mass binary because we see something probably that is a type 1 exoburst. And before I introduce the NuSTAR observation, I will introduce NuSTAR itself. The NuSTAR is a NASA mission led by Caltech. It was launched in 2012, and it is a Water 1 telescope operating in a very wide energy band of 3 to 79 keV, and which is very good for us because with FXT, we only have the energy covered up to 10 keV. And it has a very high time resolution of only 2 microseconds, which is very useful for detecting the possible pulsations from the neutron star, which we didn't. And that's it. And this is the light curve of the NuSTAR observation. We have only one observation. And at the first glance, you can already see the bursts. We detected a total of 7 bursts from NuSTAR observation. And you can see that the separation here and here are roughly the same. And even though this gap is much wider, but it seems like twice the smaller gaps. And so we did a timing analysis for the recurrence time of the bursts, that is the gap between bursts. In this figure, the x-axis is time, and the y-axis is the measured recurrence time. And each rectangle here is one data point. And the blue lines are, and we fitted, I should mention, those are 9 bursts. Those include 9 bursts around the NuSTAR observation. And we first fitted it with a constant, which is the blue lines and the area. And now we got a reduced chi-square of 8. And then we discovered the fit can be improved when you introduce a linear decrease term here, and it improved the fit statistics to a reduced chi-square of only 3. So it hints that possibly, even though the bursts are repeating very reasonably quasi-periodically, but there's a slightly decrease of the recurrence time, which we confirmed because we then realized the NuSTAR flux is also rising slowly, and it's consistent with the decrease of the recurrence time. Because if the flux is higher, it means more matter are accumulated on top of the surface during a given time. So you can expect that the next burst will come a little bit sooner. So we confirm that this source is a new clock burster, which is a very small subset of a neutron-star low-mass binaries. There are only 7 known new clock bursters before our clock burst. So ours will be the 8th clock burster. And here I show the NuSTAR light curve again, and you will see this figure many times in the program. The gray lines are the predicted time of the bursts, and you can see that basically every data point, every detected burst happens around a gray line, and the few gray lines without any detections are the ones who fall between the gaps of the data, because the data are not continuous. There are gaps in the data, and sometimes we miss a few bursts, but the one we detected happened at the time we expected. And now let's talk about eclipses. We detected a total of 10 eclipses, 8 by the FXT and 2 by NuSTAR. And we actually caught one by luck, a full eclipse during one of the FXT observations. And with the information from all the eclipses, we measured the orbital period of the system to be 6.5 hours. And the duration of the eclipse is more or less 21 minutes. Now I show the light curve again. This time I'm showing the eclipses, the expected and the detected eclipses. The blue lines and the gap between the blue lines and the red lines are the time we expect the eclipses to happen. And indeed, we detected 2 NuSTAR eclipses during this period. And now, finally, apart from the eclipses, we also observe some sudden decrease of flux in the light curves, which happen outside the expected eclipse period. And they are not caused by the companion star itself, but is likely caused by the obscuration of a bulge, which is formed at the outer part of the accretion disk. When the gas flow from the star hits the disk, we expect a bulge to be formed, and it obscures our line of sight occasionally. And even though it's way more irregular as compared to the eclipses, we do notice that even though not a very strong statistics claim, but we do notice that they seem to happen at roughly the same orbital phase. It happens almost always a bit after the eclipse, and around the in terms of orbital phase, it happens around 0.6 and 0.7. This probably tells us that the bulge is in a rather fixed place in the disk, so it always obscures the line of sight at the same position. And another thing we discovered is that we seem to only see the burst when the flux is lower, and not when the flux is higher. It can be a coincidence, yes, but if it's true, one of the reasons could be that when the flux is higher, the much stronger X-ray emissions from the inner region would produce a higher radiation pressure, which might distort or change the geometry of the bulge, making it less capable of obscuring light. And now I show the light curve for the last time. Now with the dips added, we detected 2 dips in the NuSTAR light curve, also happening a little bit after the eclipse. Here we can move on to the spectral analysis part. This is actually a joint spectral analysis with the F5C data covering the low energy band and the NuSTAR data covering the high energy band. And this cartoon I have shown before, and you can see the corresponding spectral components. Here is the smaller bump is a disk black body coming from this disk, and this more strangely shaped is a reflection spectrum, and on top of it is a containerization component, which is from the containerization of the corona. You don't see the black body from the neutron-star hot spot. It's because it's already part of the containerization spectrum. So here you only see 3 components, but the neutron-star emission is there. And this shows all the FXC spectra that we obtained. Different colors are different dates. As you can see, they are not very different. And here is the time evolution of the important spectral parameters we obtained from spectral fitting. I don't have time to go into details, but just I just want to say that this one is the flux, and you can see that the flux rise first and decrease. So there is a variation in flux, but other spectral parameters are not really very different. Like within the error, they are not really very different. So basically, we have almost a constant spectral shape, which is typical of a hard state, which is a typical hard state spectrum. And the so-called hard state is a spectral state observed in X-ray binaries, and they are characterized by a truncated disk, which is cut off far away from the neutron star, and the inner region is dominated by the corona, like shown in this cartoon. It's a hard state spectrum. And this shows the spectral analysis we did for the burst emission. And we had only one burst, which was simultaneously covered by both NuSTAR and FXT. So we have a very large bandwidth to perform a much better spectral analysis. So the x-axis is time. These are all time evolutions. This upper panel is the count rate of NuSTAR and FXT, and this is the temperature of the black body. Of the black body, and this is the normalization of the black body, which you can understand as the radius or the area of the black body emitting hotspot. And this is the flux from spectral analysis from spectrofitting. And this is the normalization of the quantized spectrum, which that's you can understand as the strength of the persistent emission. I should mention persistent emission. I mean the emission that is not a burst and not part of the eclipse, but the regular normal emission of the system. So this represents how the normal emission of the system evolves during the burst. So anyway, we didn't see any signs of a photostellar radius extension, meaning that our burst is less luminous than the Eddington value. But we do see the hints of the persistent emission evolving during the burst. I should mention the two different colors correspond to different methods we used for the model, but they are not very different. So I'm not going to introduce them. And with the spectral analysis from both the persistent part and the burst, we can measure a parameter, which is called the alpha parameter, defined as the energy released by accretion during between two bursts, the ratio of this accretion energy over the energy of the burst. And this value tells us the component, the composition of the field that was supplying to the burst. And we measured a hydrogen mass fraction of only 0.1, which means that all bursts are dominated by helium. And this is the optical observation we performed. Back in July, we were trying to find an optical instrument to observe in optical band to see if we detect the eclipses and bursts also in the optical. And it just so happens that our colleagues from our own institute, Ignacy and Jordi, were going to observe with UltraCam. It's a ultra-fast optical camera mounted on ESO's new technology telescope. It's in La Silla in Chile. And they were going to observe with UltraCam for their own project, but they were very kind and take some of their time to observe our target. So we get this very extraordinary result. And we also asked for simultaneous FXC observation. So we covered the same period with both optical and the X-ray instruments. And you can see we detected the eclipse also in optical band and in X-ray band. And there's actually a little dip here, seen also in the optical band. The eclipse duration is wavelength dependent in the sense that the more energetic the band is, usually the eclipse is shorter, which is expected because the more energetic radiations come from the more inner region of the accretion flow. And finally, we detect something not very clear here, but there's optical flare here, which is probably a stellar flare, which is common for the companion star of the system. And but we cannot fully rule out the possibility of this being a type 1 X-ray burst. We didn't see it because it was in the eclipse, but it's possible that the optical emission comes from the reprocess of the X-ray emission, which means when the X-ray emission from the type 1 X-ray burst hits the outer part of the accretion disk and even part of the star itself, it reprocesses the X-ray emission and re-emits in optical. The possibility is there. And finally, with the optical period, and we assume a neutron star mass of 1.4 solar mass, which is common for neutron stars. And we found from literature, we found empirical mass radius correlation for the stars. With all this, we can estimate the mass and the radius of the companion star, which is typical of a K-type companion, which can produce stellar flares. And this, together with the eclipse duration we measured, we can calculate the inclination of the source, which is pretty high, but it's because it's an eclipsing source. And we also tried to measure the distance of the system. I will skip we use different methods, but I will only mention the most constraining results is from the optical observation. So because we already know more or less what is the companion spectral type, so we know the absolute magnitude of the companion. And if we assume that during the eclipse, during the optical eclipse, if we assume this is emission is contributed dominantly by the companion star, then we know the apparent magnitude too. By comparing the apparent magnitude and the absolute magnitude, And considering the interstellar absorption, we can measure a distance, which is 226 kiloparsec. But the luminosity it would correspond to is kind of small. It's around 1% of the Eddington value. This is kind of small because normally we expect neutron-star low mass X binaries in outburst to have luminosities with tens of percents of the Eddington value. But one explanation for this could be that it is probably because we are viewing the source with a very high angle, and probably the outer part of the disk would obscure a majority of the emission. But it is also possible that it is intrinsically dim. And this shows the long-term monitoring light curve collected by WXT. And you can see the outburst started around June 23, and the source phase into quiescence in early August. And I should mention our work cuts from here. Like our work used the data before July 14, and the rest, and you can see the source re-brightened after we cut our data. And the rest of the data will be published in another paper by one of our collaborators, Yang Zihan from the Institute of High Energy Physics in China. Finally, I want to say thank yous to all my collaborators. It really wouldn't have been possible without their help, especially our own Alessio, Nanda, Emily, and Francesco. I probably have spent more time on this, but their contributions are definitely as important as mine. And here is a summary. I'm not going to read everything. I just want to say we discovered a new low mass X binary with the Einstein Probe, and it is pretty cool. It does all kinds of weird things, but with the help of EP, NuSTAR, and UltraCam, and many human beings, we now learned a lot about it. Thank you. Thank you.
Any questions?
Very nice talk. Thank you. Can I ask about the potential optical flare in the eclipse?
Yes.
Do you know? Can you estimate the energy with the distance that you have to see if it's more consistent with the type 1 rainbows or with the solar flare, or is the distance?
This we didn't do. Actually, we didn't really go deep into the analysis of the optical data. It's more in the timing part, but I think it's something that we can do in the future, probably after this work.
Yeah, I don't know if the distance would be. It's quite wide, right?
The duration. The duration.
No, because the distance would dictate how precise your energy would be.
Yes.
Also, can I ask about the dip?
The dip, yes.
After the eclipse.
After we don't know if it's a dip. It's probably just the variation of the optical data because it's probably the surrounding sources, and also the flux is a ratio, is a flux ratio of a star that is used as a guessing.
So it's not related to
as an example.
The X-ray dip.
Yeah. We think it's not. We think it's irrelevant for our source probably.
And would because when you see the X-ray dips at a specific phase, is that covered by the optical range or not?
The X-ray dip?
Yes, like when you have the X-ray dips at like specific phase of 0.7.
Okay. It's not the same phase. Yes.
Yes,
it's not the same.
The phase is not covered here.
Yeah. Yes.
It would be like that.
Oh, I think I see your point. You're asking if this part corresponds to the phase that we observe in X-ray. We observe the dips in the X-rays.
Yes.
Yes, I can check. I'm not pretty sure. Yes, I see your point. Thanks. I will say.
Thanks for the nice talk. And I have two questions. The first one is the technique. It looks like the calibration of the NuSTAR spectrum, is much higher than, no, not much, but is higher than EP, is it the intrinsic state difference, or it's just
because
the calibration?
the observations are happening in the same time, so it's the calibration issue. By the way, corrected in the model with a constant. We didn't show it here, but there's a constant to consider the difference of two instruments.
The second question is, given by the estimated accident ratio, looks like, and you also mentioned they have the radio counterpart. Just curious about, do they have some, because usually we see the accident ratio at 1% is a critical value for the accretion systems. They probably could have the jet launching. And I'm just curious, can you say more about the radio?
Yeah, the truth is I don't know a lot about the radio results. They are not a part of our collaboration. I saw their ATAL, and that's pretty much. But I'm not really sure if they mentioned jets in their ATAL. I can check. Thank you.
I just wanted to make a comment. This luminosity that you obtain is not so crazy actually, because if you look at atom sources in terms of being a part of the X-ray binaries, they are around those there. So around 1% energy.
Yes.
So I mean they are on the tail side of the maintenance, but not 1%. So it's very
Thank you. I think so too. And why the reason I mentioned it because it was brought up by the reviewer. But I think so. Yes. It's not impossible that it's just a dim intrinsic link.
Very much. Oh, very nice. The slide.
Sorry, this one?
33.
Okay, 33.
My there is this second decay, but it's not decay.
Sorry, which one? Which bit?
The last plot.
Yes.
The plot.
You mean this?
Yes.
And that's just a random variation of the accretion rate, and it's not a very high. It's not a very large variation because you probably can't see, but the numbers that pretty close. They are the same order of magnitude, and we know in astronomy they are the same order of magnitude and the same magnitude. Variation is not significant. That's the probably random variation of the accretion rate from the companion star, which can happen.
Yeah, the first congratulations. I don't know if you've already mentioned video testing.
I'm sorry, I didn't.
You have looked into absorption lines.
Yeah, thank you for mentioning it, but no, we didn't go into the absorption. But by absorption, I mean, I think you probably mean the X-ray, the one in the X-ray spectrum. And we thought you can see there's a feature here. It's probably an iron edge, because it's around 7 keV. And that's the most prominent thing we can see. And apart from that, we don't have too much information. In optical, we didn't do spectral analysis for the optical data, so I'm not sure. Yes, but something that we can check. Yes, the analysis of the optical data is pretty preliminary, and we basically only focus on the timing part, and the spectral analysis is not really carried out for the optical data.
But in X-ray, you probably don't have the resolution absorption line.
Yeah.
Very narrow, like you look at silicon, like the oxygen, we have narrow use, very high resolution, like the RGS is like an XMM, you can see, but resolution absorption.
Okay. Okay, thanks.
Not so bright.
Yes.
Okay, so let's thank our speaker again. Wait for the speaker.
I just
Yeah, I think we'll do. Are we good? This is your laptop.
Yeah, thank you very much.
Yeah, of course. Thank you. Very nice talk.
Muy bien,